features. And this is also doesn't change the size of the image actually. So we will go from batch channels or features, let's call it features, height width, to batch size, features, height multiplied by 2 and width multiplied by 2. Why? Because we are going to use the upsampling. This interpolation that we will do now, interpolate x scale factor equal to mode is equal to nearest, is the same operation that we did here. The same operation here. It will double the size basically. And then we apply a convolution. Now we have to define the final block, and we also have to define the output layer, and we also have to define the attention block and the residual block. So let's build first this output layer. It's easier to build. This one also has a group normalization, again with the 32 size of the group 32. Also has a convolution. And a padding of 1. Okay. The final layer needs to convert this shape into this shape, so 320 features into 4. We have a input which is batch size of 320 features. The height is divided by 8 and the width is divided by 8. We first apply a group normalization, then we apply the silu, then we apply the convolution, and then we return. This will basically, the convolution, let me write also why we are reducing the size. This convolution will change the number of channels from in to out, and when we will declare it, we say that we want to convert from 320 to 4 here. So this one will be of shape batch size 4, height divided by 4, height divided by 4, and width divided by 4 divided by 8. Then we need to go build this residual block and this attention block here. So let's build it here. Let's start with the residual block, which is very similar to the residual block that we built for the variational autoencoder. So unit block. This is the embedding of the time step. As you remember, we did the time embedding. We transform into an embedding of size of 1 to 1280. We have this group normalization. It's always this group norm. Then we have a convolution. Then we have a linear for the time embedding. Then we have another group normalization. We will see later what is this merged. and another convolution. Oops, kernel size 3, padding 1. Again, just like before, we have if the in channels is equal to the out channels, we can connect them directly with the residual connection. Otherwise, we create a convolution to connect them, to convert the size of the input into the output. Otherwise, we cannot add the two tensors. Zero. Okay. Oops. Here. So it takes in as input this feature tensor, which is actually the latent batch size in channels. Then we have height and width. And then also the time embedding, which is 1 by 1280, just like here. And we build first of all a residual connection. Then we do apply the group normalization. So usually the residual connection, the residual blocks are more or less always the same. So there is a normalization, an activation function, then we can have some skip connection, etc., etc. Then we have the time. Here we are merging the latents with the time embedding, but the time embedding doesn't have the batch and the channels dimension, so we add it here with unsqueeze and we merge them. Then we normalize this merged connection. This is why it's called merged. We apply the activation function. Then we apply this convolution, and finally we apply the residual connection. So why are we doing this? Well, the idea is that here we have three input. We have the time embedding, we have the latent, we have the prompt. We need to find a way to combine the three information together. So the unit needs to learn to detect the noise present in a noisified image at a particular time step using a particular prompt as a condition, which means that the model needs to recognize this time embedding and needs to relate this time embedding with the latency. And this is exactly what we are doing in this residual block here. We are relating the latent with the time embedding, so that the output will depend on the combination of both, not on the single noise or in the single time step. And this will also be done with the context using cross attention in the attention block that we will build now. So unit attention block. $768, okay. Okay, I will define some layers that for now will not make much sense, but later they will make sense when we make the forward method. oleorin zemela denja. So my cat is asking for food. I think he already have food, but maybe he wants to eat something special today. So let me finish this attention block and the unit, and then I'm all his. Why everyone wants attention? Self attention and head channels. Here we don't have any bias. As you remember, the self attention, we can have the bias for the W matrices. Here we don't have any bias, just like in the vanilla transformer. So we have this attention, then we have a layer normalization, self.layer norm 2, which is along the same number of features. Then we have another attention. We will see later why we need all this attention, but this is not a self attention, it's a cross attention, and we will see later how it works. Then we have the layer norm 3. This is because we are using a function that is called the JGLU activation function. So we need these matrices here. Okay, now we can build the forward method. So our x is our latency. So we have a batch size, we have a features, we have height, we have a width. Then we have our context, which is our prompt, which is a batch size, sequence length, dimension. The dimension is size 768, as we saw before. So the first thing we will do is we will do the normalization. So just like in the transformer, we will take the input, so our latency, and we apply the normalization and the convolution. Actually in the transformer there is no convolution, but only the normalization. So residue, this is called the long residual because it will be applied at the end. Okay, so we have this, we are applying the normalization, which doesn't change the size of the tensor. Then we have convolution. X is equal to self.conv input of x, which also doesn't change the size of the tensor. Then we have we take the shape, which is the size of the batch size, the number of features, the height, and the width. We transpose because we want to apply cross attention. First we apply self attention, then we apply cross attention. So we do normalization plus self attention, self attention with skip connection. So x is x dot transpose of -1 -2. So we are going from this. Wait, I forgot something here. First of all, we need to do x is equal to x dot view and c h multiplied by w. So we are going from this to batch size features and then h multiplied by w. So this one multiplied by this. Then we transpose this to dimension. So now we get from here to here. So the features become the last one. Now we apply this normalization plus self attention. So so we have a first short residual connection that will apply right after the attention. So we say that x is equal to layer norm 1, so x. Then we apply the attention, so self dot attention 1, and then we apply the residual connection. So x is plus equal to residual short, the first residual connection. Then we say that the residual short is again equal to 6, because we are going to apply now the cross attention. So now we apply the normalization plus the cross attention with skip connection. So what we did here is what we do in any transformer. So let me show you here what we do in any transformer. So we apply some normalization, we calculate the attention, and then we combine it with the skip connection here. And now we will, instead of calculating a self attention, we will do a cross attention, which we still didn't define. We will define it later. So short, and then first we apply the normalization. Then the cross attention between the latents and the prompt. This is the cross attention. So this is cross attention, and we will see how. And x plus or equal to residual short. Okay, and then again equal to x. Finally, just like with the attention the transformer, we have a feed forward layer with the JGLU activation function. And this is actually, if you watch the original implementation of the transformer of the stable diffusion, it's implemented exactly like this. So it's basically later we do a element-wise multiplication. So these are special activation functions that involve a lot of parameters. But why we use one and not the other, I told you just like before. They just saw that this one works better for this kind of application. There is no other. Then we apply the skip connection. So we apply the cross attention, then we define another one here. So this one is basically normalization plus feed forward layer with JGLU and skip connection, in which the skip connection is defined here. So at the end we always apply the skip connection. Finally, we change back to our tensor to not be a sequence of pixels anymore. So we reverse the previous transposition. Transpose 2. So basically we go from batch size width multiplied by height multiplied by width, and features into batch size features height multiplied by width. Then we remove this multiplication, so we reverse this multiplication and CHW. Finally, we will apply the long skip connection that we defined here at the beginning. So only if the size match. If the sizes don't match, we apply the here. This one we have here. Return self.conv output. And this is all of our unit. We have defined everything, I think, except for the cross attention, which is very fast. So we go to the attention that we defined before, and I put it in the wrong folder. It should be skip changes. Let me check if I put it correctly. Yeah, we only need to define this cross attention here. Okay, attention. So let's go and let's define this cross attention. So class, it will be very similar to the not very similar, actually same as the self-attention, except that the keys come from one side and the query and the query come from one side and the key and the values from another side. This is the dimension of the embedding of the keys and the values. This is the one of the queries. This is the WQ matrix. In this case, we will define instead of one big matrix made of 3 WQ, WK, and WV, we'll define 3 different matrices. Both systems are fine. You can define it as one big matrix or 3 separately. It doesn't change anything actually. So the cross is from the keys and the values. Oops, linear. Then we save the number of heads of this cross attention and also the dimension of each, how much information each head will see. And oops, the head is equal to the embed divided by the number of heads. Let's define the forward method. X is our query and Y is our keys and values. So we are relating X, which is our latent, which is of size batch size. It will have a sequence length, its own sequence length, Q, let's call it Q, and its own dimension. And the Y, which is the context or the prompt, which will be batch size, sequence len of the key V, because the prompt will become the key and the values, and each of them will have its own embedding size, dimension of kV. We can already say that this will be a batch size of 77 because our sequence length of the prompt is 77 and each embedding is of size 768. So let's build this one. This is input shape is equal to x.shape. Okay, then we have the interim shape like the same as before. So this is the sequence length, then the n number of heads, and how much information each head will see. The head. The first thing we do is multiply queries by WQ matrix. So query is equal to, then we do the same for the keys and the values, but by using the other matrices. And as I told you before, the key and the values are the Y and not the X. Again, we split them into H heads, so H number of heads. Then we transpose. I will not write the shapes because they match the same transformation that we do here. Okay, again we calculate the weight as which is the attention as query multiplied by the transpose of the keys, and then we divide it by the dimension of each head by the square root. Then we do the softmax. In this case we don't have any causal mask, so we don't need to apply the mask like before, because here we are trying to relate the tokens, so the prompt with the pixels. So each pixel can watch any word of the token, and any token can watch any pixel basically. So we don't need any mask. To obtain the output we multiply it by the V matrix, and then the output again is transposed just like before. So now we are doing exactly the same things that we did here, so transpose, reshape, etc. And then return output. And this ends our building of the, let me show you. Now we have built all the building blocks for the Stable Diffusion. So now we can finally combine them together. So the next thing that we are going to do is to create the system that, taking the noise, taking the text, taking the time embedding, will run, for example, if we want to do text to image, will run this noise many times through the unit according to a schedule. So we will build the scheduler, which means that because the unit is trained to predict how much noise is there, but we then need to remove this noise. So to go from a noisy version to obtain a less noisy version, we need to remove the noise that is predicted by the unit, and this job is done by the scheduler. And now we will build the scheduler. We will build the code to load the weights of the pre-trained model, and then we combine all these things together, and we actually build what is called the pipeline. So the pipeline of text to image, image to image, etc. And let's go. Now that we have built all the structure of the unit, or we have built the variation autoencoder, we have built a clip, we have built the attention blocks, etc. Now it's time to combine all together. So the first thing I kindly ask you to do is to actually download the pre-trained weights of the Stable Diffusion, because we need to inference it later. So if you go to the repository I shared, this one, PyTorch Stable Diffusion, you can download the pre-trained weights of the Stable Diffusion 1.5 directly from the website of Hugging Face. So you download this file here, which is the EMA, which means exponentially moving average, which means that it's a model that has been trained, but they didn't change the weights at each iteration, but with an exponentially moving average schedule. So this is good for inferencing. It means that the weights are more stable, but if you want to fine-tune later the model, you need to download this one. And we also need to download the files of the tokenizer, because of course we will give some prompt to the model to generate an image, and the prompt needs to be tokenized by a tokenizer, which will convert the words into tokens and the tokens into numbers. The numbers will then be mapped into embeddings by our clip embedding here. So we need to download two files for the tokenizer. So first of all, the weights of this one file here. Then on the tokenizer folder we find the merges.txt and the vocab.json. If we look at the vocab.json file, which I already downloaded, it's basically a vocabulary. So each token mapped to a number. That's it, just like what a tokenizer does. And then I also prepared the picture of a dog that I will be using for image to image, but you can use any image. You don't have to use the one I am using, of course. So now let's first build the pipeline, so how we will inference this stable diffusion model. And then while building the pipeline, I will also explain you how the scheduler will work. And we will build the scheduler later. I will explain all the formulas, all the mathematics behind it. So let's start. Let's create a new file. Let's call it pipeline.py. And we import the usual stuff. NumPy. NumPy as NP. We will also use the TQDM to show the progress bar. And later we will build this sampler, the DPM sampler, and we will build it later. And I will also explain what is this sampler doing and how it works, etc., etc. So first of all, let's define some constants. The stable diffusion can only accept produce images of size 512 by 512. So height is 512 by 512. The latence dimension is the size of the latence tensor of the variational autoencoder. And as we saw before, if we go check the size, the encoder of the variational autoencoder will convert something that is 512 by 512 into something that is 512 divided by 8. So the latent dimension is 512 divided by 8. And the same goes on for the height. So 512 divided by 8. We can also call it width divided by 8 and height divided by 8. Then we create a function called generate. This will be the main function that will allow us to do text to image and also image to image, which accepts a prompt, which is a string. An unconditional prompt, so unconditional prompt. This is also called a negative prompt. If you ever used Stable Diffusion, for example, with the Hugging Face library, you will know that you can also specify a negative prompt, which tells that you want, for example, you want a picture of a cat, but you don't want the cat to be on the sofa. So, for example, you can put the word sofa in the negative prompt, so it will try to go away from the concept of sofa when generating the image, something like this. And this is connected with the classifier free guidance that we saw before. So, but don't worry, I will repeat all the concept while we are building it. So this is also a string. We can have an input image in case we are building an image to image. And then we have the strength. Strength, I will show you later what is it, but it's related to if we have an input image and how much, if we start from an image to generate another image, how much attention we want to pay to the initial starting image. And we can also have a parameter called do CFG, which means do classifier free guidance. We set it to yes. CFG scale, which is the weight of how much we want the model to pay attention to our prompt. It's a value that goes from 1 to 14. We start with 7.5. The sampler name, we will only implement one, so it's called DPM. How many inference steps we want to do? And we will do 50. I think it's quite common to do 50 steps, which produces actually not bad results. The models are the pre-trained models. The seed is how we want to initialize our random number generator. Let me put a new line, otherwise we become crazy reading this. No. Okay. New line. So seed, then we have the device where we want to create our tensor. We have an idle device, which means basically if we load some model on CUDA and then we don't need the model, we move it to the CPU. And then the tokenizer that we will load later. Tokenizer is none. Okay. This is our method. This is our main pipeline that, given all this information, will generate one picture. So it will pay attention to the prompt, it will pay attention to the input image if there is, according to the weights that we have specified, so the strength and the CFG scale. I will repeat all these concepts, don't worry, later I will explain them actually how they work also on the code level. So let's start. So the first thing we do is we disable, okay, torch.notNoGrad, because we are inferencing the model. The first thing we make sure is the strength should be between 0 and 1. So if then we raise an error. Raise value error must be between 0 and 1 with idle device. If we want to move things to the CPU, we create this lambda function. Otherwise, okay. Then we create the oops, I think okay. Then we create the random number generator that we will use. I think I made some mess with this, so this one should be like here. Okay. And the generator is a random number generator that we will use to generate the noise. And if we want to start it with the seed, so if seed, then we generate with the random seed. Otherwise, we specify one manually. Let me fix this formatting because I don't know format document. Okay, now at least the then we define clip. The clip is a model that we take from the pre-trained models, so it will have the clip model inside. So this model here, basically this one here, we move it to our device. Okay, as you remember with the classifier free guidance, so let me go back to my slides. When we do classifier free guidance, we inference the model twice. First by specifying the condition, so the prompt, and another time by not specifying the condition, so without the prompt. And then we combine the output of the model linearly with a weight. This weight W is this weight here, CFG scale. It indicates how much we want to pay attention to the conditioned output with respect to the unconditioned output, which also means that how much we want the model to pay attention to the condition that we have specified. What is the condition? The prompt, the textual prompt that we have written. And the unconditioned actually is also will use the negative prompt. So the negative prompt that you use in Stable Diffusion, which is this parameter here, so unconditioned prompt, this is the unconditional output. So we will sample we will inference from the model twice, one with the prompt, one without, one with the prompt, one with the unconditioned prompt, which is usually an empty text, an empty string. And then we combine the two by this. And this will tell the model, by using this weight, we will combine the output in such a way that we can decide how much we want the model to pay attention to the prompt. So let's do it. If we want to do classifier free guidance, first convert the prompt into tokens using the tokenizer. We didn't specify what is the tokenizer yet, but later we will define it. So the conditional tokens, tokenizer, batch, encode plus. We want to encode the prompt. We want to append the padding up to the maximum length, which means that the prompt, if it's too short, it will fill up it with the paddings. And the max length, as you remember, is 77, because we have also defined it here. The sequence length is 77. And we take the input IDs of this tokenizer. Then we convert these tokens, which are input IDs, into a tensor, which will be of size, batch size, and sequence length. So conditional tokens. and we put it in the right device. Now we run it through clip, so it will convert batch size, sequence length, so these input IDs will be converted into embeddings of size 768, each vector of size 768. So let's call it dim. And what we do is conditional context is equal to clip of conditional tokens. So we are taking these tokens and we are running them through clips. So this forward method here, which will return batch size, sequence length, dimension. And this is exactly what I have written here. We do the same for the unconditioned tokens, so the negative prompt, which if you don't want to specify, we will use the empty string, which means the unconditional output of the model. So the model, what would the model produce without any condition? So if we start with random noise and we ask the model to produce an image, it will produce an image, but without any condition. So the model will output anything that it wants based on the initial noise. We convert it into tensor, then we pass it through clips, just like the conditional tokens. So it will become tokens, yes. So it will also become a tensor of size, batch size, sequence length, dimension, where the sequence length is actually always 77, and also in this case it's always 77 because it's the max length here. But I forgot to write the code to convert it into, so unconditional tokens is equal to tokenizer batch plus, so the unconditional prompt, so also the negative prompt, the padding is the same as before, so max length, and the max length is defined as 77. And we take the input IDs from here. So now we have these two prompts. What we do is we concatenate them. They will become the batch of our input to the unit. Okay. So basically what we are doing is we are taking the conditional and unconditional input and we are combining them into one single tensor. So they will become a tensor of size, batch size 2, so 2, sequence length, and dimension. Where sequence length is actually, we can already write it will become 2 by 77 by 768, because 77 is the sequence length and the dimension is 768. If we don't want to do conditional classifier free guidance, we only need to use the prompt and that's it. So we do only one step through the unit and only with the prompt, without combining the unconditional input with the conditional input. But in this case, we cannot decide how much the model pays attention to the prompt, because we don't have anything to combine it with. So again, we take just the prompt, just like before. You can take it, let's call it just tokens. And then we transform this into a tensor. Tensor long. We put it in the right device. We calculate the context, which is one big tensor. We pass it through clip, but this case it will be only one, so the batch size will be 1, so the batch dimension, the sequence is again 77 and the dimension is 768. So here we are combining two prompts, here we are combining one. Why? Because we will run through the model two prompts, one unconditioned and one conditioned, so one with the prompt that we want, one with the empty string. and the model will produce 2 output because the model takes care of the batch size. That's why we have the batch size. Since we have finished using the clip, we can move it to the idle device. This is very useful actually if you have a very limited GPU and you want to offload the models after using them. You can offload them back to the CPU by moving them to the CPU again. And then we load the sampler. For now we didn't define the sampler, but we use it and later we build it, because it's better to build it after you know how it is used. If we build it before, I think it's easy to get lost in what's happening actually. So if the sampler name is ddpm, then we build the sampler, ddpm sampler, we pass it the noise generator, and we tell the sampler how many steps we want to do for the inferencing. And I will show you later why. If the sampler is not ddpm, then we raise an error because we didn't implement any other sampler. So no sampler, let me do f sampler name. Okay. Why we need to tell him how many steps? Because as you remember, let's go here. This scheduler needs to do many steps. How many? We tell him exactly how many we want to do. So in this case, the denoisification steps will be 50. Even if during the training we have maximum of 1000 steps, during inferencing we don't need to do 1000 steps, we can do less. Of course, usually the more steps you do, the better the quality, because the more the more noise you can remove. But with the different samplers, they work in different way, and with DDPM usually 50 is good enough to get a nice result. For some other sampler, for example DDIM, you can do less steps. For some other samplers that work on with differential equations, you can do even less. Depends on which sampler you use and how lucky you are with the particular prompt actually also. This is the latence that will run through the unit, and as you know, it's of size latence height and latence width, which we defined before. So it's 512 divided by 8 by 512 divided by 8, so 64 by 64. And now let's do what happens if the user specifies an input image. So if we have a prompt, we can take care of the prompt by either running classifier free guidance, which means combining the output of the model with the prompt and without the prompt according to this scale here, or we can directly just ask the model to output only one image only using the prompt, but then we cannot combine the two output with this scale. What happens, however, if we don't want to do text to image, but we want to do image to image? If we do image to image, as we saw before, we start with an image, we encode it with the encoder, and then we add noise to it. And then we ask the scheduler to remove noise. But since the unit will also be conditioned by the text prompt, we hope that while the unit will denoise this image, it will move it towards this prompt. So this is what we will do. First of things, we load the image and we encode it and we add noise to it. So if an input image is specified, we load the encoder. We move it to the device in case we are using CUDA, for example. Then we load the tensor of the image. We resize it, we make sure that it's 512 by 512 with height, and then we transform it into a NumPy array and then into a tensor. So what will be the size here? It will be height by width by channel, and the channel will be 3. The next thing we do is we rescale this image. What does it mean? That the input of this unit should be normalized between rescaled between -1 and +1, because if we load the image, it will have 3 channels. Each channel will be between 0 and 255, so each pixel have 3 channels, RGB, and each number is between 0 and 255. But this is not what the unit wants as input. The unit wants every channel, every pixel to be between -1 and +1. So we will do this. We will build it later, this function. It's called the rescale, to transform anything from that is from between 0 and 255 into something that is between -1 and +1. And this is that will not change the size of the tensor. We add the batch dimension. On squeeze, this adds the batch dimension, batch size. Okay, and then we change the order of the dimensions, which is 0, 3, 1, 2. Why? Because as you know, the encoder of the variation autoencoder wants batch size, channel, height, and width, while we have batch size, height, width, channel. So we permute them so to obtain the correct input for the encoder. This one go into channel, and the height and width, and then this part we can delete. Okay, this is the input. Then what we do is we sample some noise, because as you remember, the encoder, to run the encoder we need some noise, and then he will sample from this particular Gaussian that we have defined before. So encoder noise, we sample it from our generator. So as you we have defined this generator so that we can define only one seed, and we can also make the output deterministic if we never change the seed. And this is why we use the generator. Latent shape. Okay, and now let's run it through the decoder. Run the image through the VA. This will produce latents. So input image tensor, and then we give it some noise. Now we are exactly here. We produced this. This is our latents. So we give the image to the encoder along with some noise. It will produce a latent representation of this image. Now we need to tell our, as you can see here, we need to add some noise to this latent. How can we add noise? We use our scheduler. The strength basically tells us, the strength parameter that we defined here tells us how much we want the model to pay attention to the input image when generating the output image. The more the strength, the more the noise we add. So the more the strength, the more the strong the noise. So the model will be more creative, because the model will have more noise to remove and can create a different image. But if we add less noise to this initial image, the model cannot be very creative, because most of the image is already defined, so there is not much noise to remove. So we expect that the output will resemble more or less the input. So this strength here basically means the more noise, how much noise to add. The more noise we add, the less the output will resemble the input. The less noise we add, the more the output will resemble the input, because the scheduler, the unit, has less possibility of changing the image, because there is less noise. So let's do it. First we tell the sampler what is the strength that we have defined, and later we will see what is this method doing, but for now we just write it. And then we ask the sampler to add noise to our latents here according to the strength that we have defined. Add noise. Basically the sampler will by setting the strength will create a time step schedule. Later we will see it, and by defining this time step schedule we will start what is the initial noise level we will start with, because if we set the noise level to be, for example, the strength to be 1, we will start with the maximum noise level. But if we set the strength to be 0.5, we will start with half noise, not all completely noise. And later this will be more clear when we actually build the sampler. So now just remember that we are exactly here. So we have the image, we compressed it with the encoder, became a latent, we added some noise to it according to the strength level, and then we need to pass it to the model, to the diffusion model. So now we don't need the encoder anymore. We can set it to the idle device. If the user didn't specify any image, then how can we start the denoising? It means that we want to do text to image. So we start with random noise. So we start with random noise. Let's sample some random noise then. Generator, and device is device. So let me write some comments. If we are doing text to image, start with random noise. Random noise defined as n01 or n0i actually. We then finally load the diffusion model, which is our unit. Diffusion, it's models. Diffusion. Later we see what is this models and how to load it. We take it to our device where we are working, so for example CUDA, and then our sampler will define some time steps. Time steps basically means that, as you remember, to train the model we have maximum of 1000 time steps, but when we inference we don't need to do 1001 steps. In our case we will be doing, for example, 50 steps of inferencing. If the maximum strength level is 1000, for example, if the maximum level is 1000, the minimum level will be 1, or if the maximum level is 999, the minimum will be 0. And this is a linear time steps. If we do only 50, it means that we need to do, for example, we start with 1000 and then we do every 20. So 980, then 960, 940, 920, 900, then 800, 880, 860, 840, 820, etc., etc., until we arrive to the 0th level. Basically, each of these time steps indicates a noise level. So when we denoise the image, or the initial noise in case we are doing the text to image, we can tell the scheduler to remove noise according to particular time steps, which are defined by how many inference steps we want. And this is exactly what we are going to do now. When we initialize the sampler, we tell him how many steps we want to do, and he will create this time step schedule. So according to how many we want. And now we just go through it. So we tell the time steps. We create TQDM, which is a progress bar. We take the time steps. And for each of these time steps, we denoise the image. So we have 300. This is our, we need to tell the unit, as you remember, diffusion. The unit has as input the time embedding. So what is the time step we want to denoise? The context, which is the prompt, or in case we are doing a classifier-free guidance, also the unconditional prompt, and the latent, the current state of the latent. Because we will start with some latent and then keep denoising it and keep denoising it, keep denoising it according to the time embedding, to the time step. So we calculate first the time embedding, which is an embedding of the current time step. and we will obtain it from this function. Later we define it. This function basically will convert a number, so the time step, into a vector, one of size 320, that describes this particular time step. And as you will see later, it's basically just equal to the positional encoding that we did for the transformer model. So in the transformer model, we use the sines and the cosines to define the position. Here we use the sines and cosines to define the time step. And let's build the model input, which is the latence, which is of shape batch size 4, because it's the input of the encoder of the variation autoencoder, which is of size 4. Which has 4 channels, and then has latence height, and the latence width, which is 64 by 64. Now, if we do this one, we need to send. Basically, we are sending the conditioned. Where is it? Here. We send the conditional input, but also the unconditional input if we do the classifier free guidance, which means that we need to send the same latent with the prompt and without the prompt. And so what we can do is we can repeat this latent twice if we are doing the classifier free guidance. It will become model input by repeat on 1. This will basically transform batch size 4. So this is going to be twice the size of the initial batch size, which is 1 actually, and 4 channels, and latence height and latence width. So basically we are repeating this dimension twice. We are making 2 copies of the latence. One will be used with the prompt, one without the prompt. So now we check the model output. What is the model output? It is the predicted noise by the unit. So the model output is the predicted noise by the unit. We do diffusion, model input, context, and time embedding. And if we do classifier free guidance, we need to combine the conditional output and the unconditional output. Because we are passing the input of the model, if we are doing classifier free guidance, we are giving a batch size of 2, the model will produce an output that has batch size of 2. So we can then split it into 2 different tensors. One will be the conditional and one will be the unconditional. So the output conditional and the output unconditional are splitted in this way using chunk. The dimension is along the 0th dimension, so by default it's the 0th dimension. And then we combine them according to this formula here. Where is the... I miss out. According to this formula here, so unconditional output minus the conditioned output minus the unconditioned output multiplied by the scale that we defined plus the unconditioned output. So the model output will be conditioned scale multiplied by the output conditioned minus the output unconditioned plus the output unconditioned. And then what we do is basically, okay, now comes the, let's say, the clue part. So we have a model that is able to predict the noise in the current latency. So we start, for example, imagine we are doing text to image. So let me go back here. We are going text to image is here. So we start with some random noise and we transform into latence. Then according to some scheduler, according to some time step, we keep denoising it. Now our unit will predict the noise in the latence. But how can we remove this noise from the image to obtain a less noisy image? This is done by the scheduler. So at each step, we ask the unit how much noise is in the image. We remove it, and then we give it again to the unit and ask how much noise is there, and we remove it. And then ask again how much noise is there, and then we remove it. And then how much noise is there, and then we remove it. Until we finish all these time steps. After we have finished these time steps, we take the latent, give it to the decoder, which will build our image. And this is exactly what we are doing here. So imagine we don't have an input image, so we have some random noise. We define some time steps on this sampler based on how many inference steps we want to do. We do all this time step. We give the latents to the unit. The unit will tell us how much is the predicted noise, but then we need to remove this noise. So let's do it. So let's remove this noise. So the latents are equal to sampler dot step time step latents model output. This basically means take the image from a more noisy version. Okay, let me write it better. Remove noise predicted by the unit. Okay. And this is our loop of denoising. Then we can do to idle diffusion. Now we have our denoised image because we have done it for many steps. Now what we do is we load the decoder, which is models decoder, and then our image is run through the decoder. So we run the latents through the decoder. So we do this step here. So we run this latent through the decoder. This will give the image. It actually will be only one image because we only specify one image. Then we do images is equal to, because the image was initially, as you remember here, it was rescaled. So from 0 to 255 in a new scale that is between 0, -1 and +1. Now we do the opposite step. So rescale again from -1 to 1 into 0 to 255 with clamp equal true. Later we will see this function. It's very easy. It's just a rescaling function. We permute because to save the image on the CPU, we want the channel dimension to be the last one. Permute 0 to 3 1. So this one basically will take the batch size, channel height width into batch size, height width channel, and then we move the image to the CPU. And then we convert it into a NumPy array, and then we return the image. Voila. Let's build this rescale method. So what is the old range? What is the new range? And the clamp. So let's define the old minimum. Old maximum is the old range. New minimum and new maximum, new range, minus equal to old min, x multiply equal to new max minus new min divided by old max minus old min, x plus equal to new min. We are just rescaling, so convert something that is within this range into this range. And if it's clamp, then x is equal to x dot clamp, new min, new max, and then we return x. Then we have the time embeddings, the method that we didn't define here, this get time embedding. This means basically take the time step, which is a number, so which is an integer, and convert it into a vector of size 320. And this will be done exactly using the same system that we use for the transformer for the positional embeddings. So we first define the frequencies of our cosines and the sines exactly using the same formula of the transformer. So if you remember, the formula is equal to the 10,000 1 over 10,000 to the power of something, of I remember correctly. So it's power of 10,000 and minus torch dot arrange. So I am referring to this formula just in case you forgot. Let me find it using the slides. I am talking about this formula here. So the formula that defines the positional encodings here. Here we just use a different dimension of the embedding. This one will produce something that is 160 numbers, and then we multiply it. We multiply it with the time step. So we create a shape of size 1. So x is equal to torch dot tensor, which is a single time step of t type. Take everything, we add one dimension. So we add one dimension here. This is like doing an unsqueeze multiplied by the frequencies, and then we multiply this by the sines and the cosine, just like we did in the original transformer. This one will return a tensor of size 100 by 62, so which is 320, because we are concatenating two tensors. Not cosine, but sine of x, and then I concatenated along the dimension, the last dimension. And this is our time embedding. So now let's review what we have built here. We built basically a system, a method that takes the prompt, the unconditional prompt, also called the negative prompt, the prompt or empty string, because if we don't want to use any negative prompt, the input image, so what is the image we want to start from in case we want to do an image to image, the strength is how much attention we want to pay to this input image when we denoise the image, or how much noise we want to add to it basically. And the more noise we add, the less the output will resemble the input image. If we want to do classifier free guidance, which means that if we want the model to output two output, one is the output with the prompt and one without the prompt, and then we can adjust how much we want to pay attention to the prompt according to this scale. And then we defined the scheduler, which is only one, the DPM, and we will define it now, and how many steps we want to do. The first thing we do is we create a generator, which is just a random number generator. Then the second thing we do is, if we want to do classifier free guidance, as we need to do basically we need to go through the unit twice, one with the prompt, one without the prompt. The thing we do is that actually we create a batch size of two, one with the prompt and one without the prompt, or using the unconditioned prompt or the negative prompt. In case we don't do the classifier free guidance, we only build one tensor that only includes the prompt. The second thing we do is we load, if there is an input image, we load it. So instead of starting from random noise, we start from an image to which we add the noise according to the strength we have defined. Then for the number of steps defined by the sampler, which are actually defined by the number of inference steps we have defined here, we do a loop, a for loop. That for each for loop, let me go here. The unit will predict some noise, and the scheduler will remove this noise and give a new latent. Then this new latent is fed again to the unit, which will predict some noise, and we remove this noise according to the scheduler. Then we again predict some noise, and we remove some noise. The only thing we need to understand is how we remove the noise from the image now, because we know that the unit is trained to predict the noise, but how do we actually remove it? And this is the job of the scheduler. So now we need to go build this scheduler here. So let's go build it. Let's start building our ddpm scheduler. So ddpm.py. Oops, I forgot to put it inside the folder. And let me review one thing. Yeah, this is wrong. Okay. So import torch, import numpy, and let's create the class ddpm sampler. Okay, I didn't call it scheduler because I don't want you to be confused with the beta schedule, which we will define later. So I call it scheduler here. Oops, why I opened this one? I call it scheduler here, but actually I mean the sampler, because there is the beta schedule that we will define now. What is the beta schedule? Which indicates the amount of noise at each time step, and then there is what is known as the scheduler or the sampler. From now on I will refer it to as sampler. So this scheduler here actually means a sampler. I'm sorry for the confusion. I will update the slides when the video is out. So how much were the training steps? Which is 1000. The beta is okay. Now I define two constants, and later I define them, what are they and where they come from. 0.85 and beta end. It's a floating point of 0.0120. Okay. The parameter beta start and beta end, basically, if you go to the paper, if we look at the forward process, we see that the forward process is the process that makes the image more noisy. We add noise to the image. So given an image that don't have less noise, how to get a more noisy image? According to this Gaussian distribution, which is actually a chain of Gaussian distribution, which is called a Markov chain of Gaussian distributions. And the noise that we add varies according to a schedule, variance schedule, beta 1, beta 2, beta 3, beta 4, beta t. So beta, basically, it's a series of numbers that indicates the variance of the noise that we add with each of these steps. And as in the stable diffusion, they use a beta start, so the first value of beta is 0.0085, and the last variance, so the beta that will turn the image into complete noise, is equal to 0.0120. It's a choice made by the authors, and it's a linear, we will use a linear schedule. Actually, there are other schedules which are, for example, the cosine schedule, etc., but we will be using the linear one. And we need to define this beta schedule, which is actually 1000 numbers between beta start and beta end. So let's do it. So this is defined using the linear space, where the starting number is beta start actually to the square root of beta start. So square root of beta start, because this is how they define it in the stable diffusion. If you check the official repository, they will also have these numbers and defined in exactly the same way. 0.5, then the number of training steps, so in how many pieces we want to divide this linear space, beta end, and then the type is torch.float32, I think, and then to the power of 2, because they do they divide it into 1000 and then to the power of 2. This is in the diffusers libraries from Hugging Face. I think this is called the scaled linear schedule. Now we need to define other constants that are needed for our forward and our backward process. So our forward process depends on this beta schedule, but actually this is only for the single step. So if we want to go from, for example, the original image by one step forward of more noise, we need to apply this formula here. But there is a closed formula here called this one here that allows you to go from the original image to any noisified version of the image at any time step between 0 and 1000 using this one here, which depends on alpha bar that you can see here, so the square root of this alpha bar, and the variance also depends on this alpha bar. What is alpha bar? Alpha bar is the product of alpha going from 1 up to t. So if we are, for example, we want to go from the time step 0, which is the image without any noise, to the time step 10, which is the image with some noise. And remember that time step 1000 means that it's only noise. So we want to go to time step 10, which means that we need to calculate this AS of 1, AS1, AS2, AS3, AS2, and up until AS10. And we multiply them together. This is the productory. And this A, what is this alpha? This alpha actually is 1 minus beta. So let's calculate these alphas first. So alpha is actually 1 minus beta. Beta, self dot betas. So it becomes floating. And then we need to calculate the product of these alphas from 1 to t. And this is easily done with the PyTorch. We pre-compute them basically. This is also comprod self.alphas. This will create basically an array where the first element is the first alpha. So alpha, for example, 0. The second element is alpha 0 multiplied by alpha 1. The third element is alpha 0 multiplied by alpha 1 multiplied by alpha 2, etc. So it's a cumulative product, we say. Then we create one tensor that represents the number 1, and later we will use it. Tensor 1.0. Okay, we save the generator. We save the number of training steps. And then we create the time step schedule. The time step basically, because we want to reverse the noise, we want to remove noise, we will start from the more noisy to less noise. So we will go from 1000 to 0 initially. So let's say time steps is equal to torch from we reverse this. So this is from 0 to 1000, but actually we want 1000 to 0. And this is our initial schedule in case we want to do 1000 steps. But later, because here we actually specify how many inference steps we want to do, we will change these time steps here. So if the user later specifies less than 1000, we will change it. So let's create the method that will change these time steps based on how many actual steps we want to make. So set inference step time steps. As I said before, we usually perform 50, which is also actually the one they use normally for example, in Hugging Face library. Let's save this value because we will need it later. Now, if we have a number, for example, we go from 1000. Actually, it's not from. This is not from 0 to 1000, but it's from 0 to 1000 minus 1 because this is excluded. So it will be from 99, 999, 998, 997, 996, etc. up to 0. So we have 1000 numbers, but we don't want 1000 numbers, we want less. We want 50 of them. So what we do is basically we space them every 20. So we start with 999, then 999 minus 20, then 999 minus 40, etc., etc., until we arrive to 0. But in total, here will be 1000 steps, and here will be 50 steps. Why minus 20? Because 20 is 1000 divided by 50, if I'm not mistaken. So this is exactly what we are going to do. So we calculate the step ratio, which is self.num training step divided by how many we actually want. And we redefine the time steps according to how many we actually want to make. Zero num inference steps multiplied by this step ratio and round it. We reverse it just like before, because this is from 0. So this is actually means 0, then 20, then 40, then 60, etc. until we reach 999. Then we reverse it. Then copy as type int np dot int 64, so a long one, and then we define as tensor. Now the code looks very different from each other because actually I have been copying the code from multiple sources. Maybe one of them I think I copied from the Hugging Face library, so I didn't change it. I kept it to the original one. Okay, but the idea is the one I showed you before. So now we set the exact number of time steps we want, and we redefine this time steps array like this. Let's define the next method, which basically tells us, let's define the method on how to add noise to something. So imagine we have the image. As you remember, to do image to image, we need to add noise to this latent. How do we add noise to something? Well, we need to apply the formula as defined in the paper. So let's go in the paper here. We need to apply this formula here. And that's it. This means that given this image, I want to go to the noisified version of this image at time step t, which means that I need to take we need to have a sample from this Gaussian, but we don't okay, let's build it, and we will apply the same trick that we did for the variational autoencoder. As you remember, in the variational autoencoder I actually already showed how we sample from a distribution of which we know the mean and the variance. Here we will do the same here. But of course we need to build the mean and the variance. What is the mean of this distribution? It's this one. And what is the variance? It's this one. So we need to build the mean and the variance, and then we sample from this. So let's do it. ddpm. So we take the original samples, which is the float tensor, and then the time steps. So this is actually time step, not time steps. It indicates at what time step we want to add the noise, because you can add the time step at the noise at time step 1, 2, 3, 4 up to 1000, and with each level the noise increases. So the noisified version at time step 1 will be not so noisy, but at the time step 1000 will be complete noise. This returns a float tensor. Okay, let's calculate first. Let me check what we need to calculate first. We can calculate first the mean and then the variance. So to calculate the mean, we need this alpha cum prod, so the cumulative prod of the alpha, which stands for alpha bar. So the alpha bar, as you can see, it's the cumulative product of all the alphas, which is each alpha is 1 minus beta. So we take this alpha bar, which we will call alpha cum prod, so it's already defined here. Alpha cum prod is self dot to device. We move it to the same device because we need to later combine it with it. And of the same type. This is a tensor that we also move to the same device of the other tensor. Now we need to calculate the square root of alpha bar. So let's do it. Square root of alpha cumprod, or alpha prod, is alpha cumprod at the time step t to the power of 0.5. Why to the power of 0.5? Because having a number to the power of 0.5 means doing the square root of the number, because it's the square root of 1/2, which becomes the square, to the power of 1/2, which becomes the square root. And then we flatten this array. And then basically, because we need to combine this alpha cumprod, which doesn't have dimensions, it only has one dimension, which is the number itself, but we need to combine it with the latents, we need to add some dimensions. So one trick is to just keep adding dimensions with unsqueeze until you have the same number of dimensions. So until the then of sqrt shape is less than most of this code I have taken from the Hugging Face libraries samplers. So we keep adding dimension until this one and this tensor and this tensor have the same dimensions. This is because otherwise we cannot do broadcasting when we multiply them together. The other thing that we need to calculate this formula is this part here, 1 minus alpha bar. So let's do it. So sqrt of 1 minus alpha prod, as the name implies, is 1 minus alpha cumprod at the time step t to the power of 0.5. Why 0.5? Because we don't want the variance, we want the standard deviation, just like we did with the encoder of the variational autoencoder. We want the standard deviation because, as you remember, if you have an n01 and you want to transform into an n with a given mean and a variance, the formula is x is equal to mean plus the standard deviation multiplied by the n01. Let's go back. So this is the standard deviation. And we also flatten this one. And then again we keep adding the dimensions until they have the same dimension, otherwise we cannot multiply them together or sum them together. Unsqueeze, so we keep adding dimensions. Now as you remember, our method should add noise to an image. So we need to add noise, means we need to sample some noise. So we need to sample some noise from the n01. Using this generator that we have. I think my cat is very angry today with me because I didn't play with him enough. So later, if you guys excuse me, I need to later play with him. I think we will be done very soon. So let's get the noisy samples using the noise and the mean and the variance that we have calculated according exactly to this formula here. So we do the mean. Actually no, the mean is this one multiplied by x0. So the mean is this one multiplied by x0 is the mean. So we need to take this square root of alpha cumprod multiplied by x0, and this will be the mean. So the mean is square root of alpha prod multiplied by the original latent, so x0, so the input image or whatever we want to noisify, plus the standard deviation, which is a square root of this one multiplied by a sample of the from the n01, so the noise. And this is how we noisify an image. This is how we add noise to an image. So this one, let me write it down. So all of this is according to the equation 4 of the DDM paper, and also according to this. Okay, now that we know how to add noise, we need to understand how to remove noise. So as you remember, let's review again. Here, imagine we are doing text to text or text to image or image to image, it doesn't matter. The point is our unit, as you remember, is trained to only predict the amount of noise given the latent with noise, given the prompt, and the time step at which this noise was added. So what we do is we have this predicted noise from the unit. We need to remove this noise. So the unit will predict the noise, but we need some way of removing the noise to get the next latent. What I mean by this is you can see this reverse process here. So the reverse process is defined here. We want to go from xt, so something more noisy, to something less noisy based on the mu, or anyway, based on the noise, not on the mu, sorry, based on the noise that was predicted by the unit. But here in this formula, you don't see any relationship to the noise predicted by the unit. Actually, here it just says if you have a network that can evaluate this mean and this variance, you know how to remove the noise, to how to go from xt to xt minus 1. But we don't have a method that actually predicts the mean and the variance. We have a method that tells us how much noise is there. So the formula we should be looking at is actually here. So here, because we have we trained our network, our unit, as a epsilon theta. As you remember, our training method was this. We do gradient descent on this loss, in which we train a network to predict the noise in a noisy image. So we need to use this epsilon theta now to remove the noise. So this predicted noise to remove the noise. And if we read the paper, it's written here that to sample xt minus 1 given xt is to compute xt minus 1 is equal to this formula here. This tells us how to go from xt to xt minus 1. And this is the, so basically we sample some noise, we multiply it by this sigma, and this basically reminds us on how to go from the n01 to any distribution with a particular mean and a particular variance. So we will be working according to this formula here actually, because we have a model that predicts noise. Here, this epsilon theta, and this is our unit. The unit is trained to predict noise. So let's build this part now, and I will, while building it, I will also tell you which formula I'm referring to at each step, so you can also follow the paper. So now let's build the method. Let's call step method that, given the time step at which the noise was added, or we think it was added, because when we do the reverse process, we can also skip. It's not we think it was added, but we can skip some time steps. So we need to tell him what is the time step at which it should remove the noise. The latents, so as you know, the unit works with latents, so with this z's here, so this is z, and it keeps denoising, so the latents. And then what is the model output? So the predicted noise of the unit. So the model output is the predicted noise. Torch.tensor. This model output corresponds to this epsilon theta of xt. So this is the predicted noise at time step t. This latency is our xt. And what else we need? The alpha we have, the beta we have everything. Okay, let's go. So t is equal to time step. The previous t is equal to self.get previous time step t. This is a function that, given this time step, calculates the previous one. Later we will build it. Actually, we can build it now. It's very simple. Okay. Get previous time step self time step, which is an integer. We return another integer. previous time step is equal to the time step minus self minus basically this quantity here, step ratio. So self dot num training steps divided by self dot num inference steps return previous t. This one will return basically given for example the number 999, it will return number 999 minus 20 because the time steps for example the initial time step will be, suppose it's 1000, the training steps we are doing is 1000 divided by the number of inference step which is we will be doing is 50, so this is means 1000 minus 20 because 1000 divided by 50 is 20, so it will return 980. When we give him a 980 as input, he will return 960. So what is the next step that we will be doing in our for loop, or what is the previous step of the denoising? So we are going from the image noised at the time step 1000 to an image noised at the time step 980, for example. This is the meaning of previous step. Then we retrieve some data. Later we will use it. So alpha pod t is equal to self dot alpha. For now, if you don't understand, don't worry, because later I will write, I will just collect some data that we need to calculate a formula, and then I will tell you exactly which formula we are going to calculate. Alpha prod t prev. If we don't have any previous step, then we don't know which alpha to return, so we just return 1. And actually, there is a paper that came out, I think, from ByteDance that was complaining that this method of doing is not correct because the last time step doesn't have this doesn't have the signal to noise ratio about equal to 0. But okay, this is something we don't need to care about now. Actually, if you're interested, I will link the paper in the comments. Prev current alpha t prod t divided by alpha prod prev current. Also, this code I took it from Hugging Face diffusers library because I mean we are applying formulas, so even if I wrote it by myself, it wouldn't be any different because we are just applying formulas from the paper. So the first thing we need to do is to compute the original sample according to the formula 15 of the paper. What do I mean by this? As you can see, where is it? This one. Where is it? Here. So actually, let me show you another formula here. As you can see, we can calculate the previous step, so the less noisy, the forward process, sorry, the reverse process. We can calculate the less noisy image given a more noisy image and the predicted image at time step 0 according to this formula here, where the mean is defined in this way and the variance is defined in this way. But what is the predicted x0? So given an image, given a noisy image at time step t, how can we predict what is the x0? Of course, this is the predicted x0, not what will be the x0. So this predicted x0, we can also retrieve it using the formula number 15, if I remember correctly. It's here. So this x0 is given as xt minus 1 minus alpha multiplied by the predicted noise at time step t divided by the square root of alpha. All these quantities we have. So actually there are two ways which are equivalent to each other actually numerically of going from more noisy to less noisy. One way is this one here, which is the algorithm 2 of the sampling, and one is this one here, so the equation number 7, that allows you to go from more noisy to less noisy, but the two are numerically equivalent. They just in the effect they are equivalent. It's just they have different parameterization, so they have different formulas. So as a matter of fact, for example, here in the code they say to go from xt to xt minus 1 you need to do this calculation here, but as you can see, for example, this numerator of this multiplied by this epsilon theta is different from the one in the algorithm here, but actually they are the same thing, because bt is equal to 1 minus alpha t, as alpha is defined as 1 minus beta, as you remember. So there are multiple ways of obtaining the same thing. So what we will do is we will apply this formula here, in which we need to calculate the mean and we need to calculate the variance according to these formulas here, in which we know alpha, we know beta, we know alpha bar, we know all the other alphas we know, because there are parameters that depend on beta. What we don't know is x0, but x0 can be calculated as in the formula 15 here. So first we will calculate this x0, predicted x0. So first compute the predicted original sample using formula 15 of the DDPM paper. Predicted original sample latents minus, so we do latents minus the square root of 1 minus alpha t. What is the square root of 1 minus alpha t? Is equal to beta. So I have here beta t, which is already 1 minus alpha t, as you can see. Alpha bar, 1 minus alpha bar at the time step t, because I already retrieve it from here. So beta to the power to the power of 1/2, or the square root of beta. So we do latents minus beta prod at time step t to the power of 0.5, which it means basically square root of beta, and then we multiply this by the predicted noise of the image of the latent at time step t. So what is the predicted noise? It's the model output, because our unit predicts the noise, model output, and then we need to divide this by, let me check, square root of alpha t, which we have, I think, here, alpha t here. So the square root of alpha t, alpha prod t to the power of 0.5. Here I have something, this one I don't need, this one I don't need, okay, because otherwise it's wrong, right? Yeah, first there is a product between these two terms, and then there is the difference. Yeah, okay. This is how we compute the prediction, the x0. Now let's go back to the formula number 7. 7. Okay, now we have this x0, so we can compute this term, and we can compute this term, and we can compute this term, and all the other terms we also can compute. So we calculate this mean and this variance, and then we sample from this distribution. So compute the coefficients for bread original sample and the current sample xt. This is the same comment that you can find on the diffusers library, which basically means we need to compute this one. This is the coefficient for the predicted sample, and this is the coefficient for xt, this one here. So predicted original sample coefficient, which is equal to what? Alpha prod t minus 1, so the previous alpha prod t, which is alpha prod t previous, which means the alpha prod t but at the previous time step, under the square root, so to the power of 0.5 multiplied by the current beta t, so the beta at the time step t, so current beta t, which is we define it here, current beta t, we retrieve it from alpha, we could have a okay, and then we divide it by beta product t, because 1 minus alpha bar is actually equal to beta bar. beta product t. Then we have this coefficient here, so this one here. So this is current sample coefficient is equal to current alpha t to the power of 0.5, which means the square root of this time, this thing here, so the square root of alpha t. And then we multiply it by beta at the previous time step, because it's 1 minus alpha at the previous time step corresponds to beta at the previous time step, multiplied by beta prod t prev divided by beta at the time step t, so beta prod t. Now we can compute the mean. So the mean is the sum of these two terms, prev sample. So let me write some here. Compute the predicted previous sample mean mudity is equal to predicted original sample coefficient multiplied by what? By x0. What is x0? Is this one that we obtained by the formula number 15. So the predicted original sample, so x0 plus this term here. What is this term? Is this one here, so the current sample coefficient multiplied by xt. What is xt? Is the latence at the time step t. Now this we have computed the mean for now. We need to compute also the variance. Let's create another method to compute the variance. Def get variance self time step int. Okay, we obtained the previous time step t because we need to do for later calculations. Again, we calculate the alpha prod t. So all the terms that we need to calculate these particular terms here. And the current beta t is equal to 1 minus alpha prod t divided alpha prod this one. What is current beta t is equal to 1 minus alpha prod t. Yeah, 1 minus alpha prod t divided by alpha prod t0. Okay. So the variance, according to the formula number 6 and 7, so this formula here, is given as 1 minus alpha prod t prev, so 1 minus alpha prod t prev divided by 1 minus alpha prod, which is 1 minus alpha prod. Why prod? Because this is the alpha bar, and multiplied by the current beta t. And beta t is defined, I don't remember where, it's 1 minus alpha. And this is our variance. We clamp it. Oops. Torch.clamp variance. And the minimum that we want is 1 equal to minus 20 to make sure that it doesn't reach 0. And then we return the variance. And now that we have the mean and the variance, so this variance has also been computed using, let me write here, computed using formula 7 of the DDPM paper. Now we go back to our step function. So what we do is equal to 0. So because we only need to add the variance if we are not at the last time step. If we are at the last time step, we have no noise, so we don't add any. We don't need to add any noise actually, because the point is we are going to sample from this distribution, and just like we did before, we actually sample from the n01 and then we shift it according to the formula. So the n Gaussian with the particular mean and the particular variance is equal to the Gaussian at 0, 1 multiplied by the standard deviation plus the mean. So we sample the noise. Okay, we sample some noise, compute the variance. Actually, this is the variance already multiplied by the noise, so it's actually the standard deviation, because we will see self dot get variance at the time step t to the power of 0.5. So this had 0.5. So this one becomes the standard deviation. We multiply it by the n01. So what we are doing is basically we are going from n01 to n with a particular mu and a particular sigma, using the usual trick of going from x is equal to the mu plus the sigma. Actually not, yeah, this is the sigma squared then, because this is the variance, sigma multiplied by the z, where z is distributed according to the n01. This is the same thing that we always done also for the variation autoencoder, also for adding the noise, the same thing that we did before. This is how you sample from a distribution, how you actually shift the parameter of the Gaussian distribution. So predicted prev sample is equal to the predicted prev sample plus the variance. This variance term here already includes the sigma multiplied by z. And then we return predicted prev sample. Oh, okay. Now we have also built the sampler. Let me check if we have everything. No, we missed still something, which is the set strength method. As you remember, when we want to do image to image, so let's go back to check our slides. If we want to do image to image, we convert the image using the VA to a latent. Then we need to add noise to this latent, but how much noise we can decide. The more noise we add, the more freedom the unit will have to change this image. The less noise we add, the less freedom it will have to change the image. So what we do is basically, by setting the strength, we make our sampler start from a particular noise level. And this is exactly what the method we want to implement. So I made some mess. Okay, so for example, as soon as we load the image, we set the strength, which will shift the noise level from which we start from, and then we add noise to our latent to create the image to image here. So let's go here and we create this method called set strength. Okay, the start step, because we will skip some steps, is equal to self.num inference steps minus int of self-num inference. This basically means that if we have 50 inference steps and we set the strength to, let's say, 0.8, it means that we will skip 20% of the steps. So when we will add, we will start from image to image, for example, we will not start from a pure noise image, but we will start from 80% of noise in this image. So the unit will still have freedom to change this image, but not as much as with 100% noise. We redefine the time steps because we are altering the schedule. So basically we skip some time steps. And self.start step is equal to start step. So Actually, what we do here is, suppose we have the strength of 80%, we are actually fooling the method, the unit, into believing that he came up with this image, which is now with this level of strength, and now he needs to keep denoising it. This is how we do image to image. So we start with an image, we noise it, and then we make the unit believe that he came up with this image with this particular noise level, and now he has to keep denoising it until, according of course also to the prompt, until we reach the clean image without any noise. Now we have the pipeline that we can call, we have the DDPM sampler, we have the model built. Of course we need to create the function to load the weights of this model. So let's create another file. We will call it the model loader. Here, model loader, because now we are nearly close to sampling from this, finally from this stable diffusion. So now we need to create the method to load the pre-trained weights that we have downloaded before. So let's create it. Import clip encoder, VA encoder, then from decoder import VA decoder, fusion, import diffusion, our diffusion model, which is our unit. Now let me first define it, then I tell you what we need to do. So preload models from standard weights. Okay, as usual we load the weights using torch, but we will create another function, model converter dot load from standard weights. This is a method that we will create later to load the weights, the pre-trained weights, and I will show you why we need this method. Then we create our encoder, and we load the stateDict. Load stateDict from our stateDict, and we also set strict to load stateDict. Strict true. Then we have the decoder, and it's strict also. So this strict parameter here basically tells that when you load a model from PyTorch, this, for example, this CKPT file here, it is a dictionary that contains many keys, and each key corresponds to one matrix of our model. So, for example, this this group normalization has some parameters, and how can Torch load these parameters exactly in this group norm? By using the name of the variables that we have defined here, and he will, when we load a model from PyTorch, he will actually load a dictionary, and then we load this dictionary into our models, and he will match by names. Now the problem is the pre-trained model, actually they don't use the same name that I have used, and actually this code is based on another code that I have seen. So actually the names that we use are not the same as the pre-trained model. Also because the names in the pre-trained model not always very friendly for learning. This is why I changed the names, and also other people changed the names of the methods. But this also means that the automatic mapping between the names of the pre-trained model and the names defined in our classes here cannot happen, because it cannot happen automatically because the names do not match. For this reason, there is a script that I have created in my GitHub library here that you need to download to convert these names. It's just a script that maps one name into another. So if the name is this one, map it into this. If the name is this one, map it into this. There is nothing special about this script. It's just a very big mapping of the names. And this is actually done by most models because if you want to change the name of the classes or the variables, then you need to do this kind of mapping. So I will also I will basically copy it. I don't need to download the file. So this will call the model converter.py, model converter.py, and that's it. It's just a very big mapping of names, and I take it from this comment here on GitHub. So this is model converter. So we need to import this model converter. Import model converter. This model converter basically will convert the names, and then we can use the load state dict, and this will actually map all the names. And so now the names will map with each other, and this strict makes sure that if there is even one name that doesn't map, then throw an exception, which is what I want, because I want to make sure that all the names map. So we define the diffusion and we load its state dict. Diffusion and strict equal to true, and let me check. Oops. Then we do clip is equal to clip.to device, so we move it to the device where we want to work, and then we load also his state dict, so the parameters, so the weights. And then we return a dictionary. Clip, and then we have the encoder. Is the encoder. We have the decoder. Is the decoder, and then we have the diffusion, etc. Now we have all the ingredients to run finally the inference, guys. So thank you for being patient so much, and it's really finally we can see the light coming. So let's build our notebook so we can visualize the image that we will build. Okay, let's select the kernel. Stable diffusion, I already created it. In my repository you will also find the requirements that you need to install in order to run this. So let's import everything that we need. So the model loader, the pipeline, pil import image. This is how to load the image from Python. So pathlib import, actually this one we don't need. Transformers. This is the only library that we will be using because it's the tokenizer of the clip. So how to tokenize the text into tokens before sending it to the clip embeddings. Otherwise we also need to build the tokenizer, and it's really a lot of job. I don't allow CUDA, and I also don't allow MPS. But you can activate these two variables if you want to use CUDA or MPS. Available and allow CUDA, then the device becomes CUDA, of course. And then we printed the device we are using. Okay, let's load the tokenizer. tokenizer is the clip tokenizer. We need to tell him what is the vocabulary file, so which is I already saved here in the data vocabulary.json, and then also the merges file. Maybe one day I will make a video on how the tokenizer works, so we can build also the tokenizer, but this is something that requires a lot of time, I mean, and it's not really related to the diffusion model, so that's why I didn't want to build it. The model file is, I will use the data and then this file here. Yeah. Then we load the model. So the models are model loader dot preload model from the model file into this device that we have selected. Okay, let's build from text to image. What we need to define? The prompt. For example, I want a cat sitting or stretching, let's say stretching on the floor, highly detailed. We need to create a prompt that will create a good image, so we need to add a lot of details: ultra sharp, cinematic, etc, etc. 8K resolution. The unconditioned prompt, I keep it blank. This you can also use it as a negative number. You can use it as a negative prompt. So if you don't want the output to have some, how to say, some characteristics, you can define it in the negative prompt. Of course, I like to do CFG, so the classifier free guidance, which we set to true. CFG scale is a number between 1 and 14, which indicates how much attention we want the model to pay to this prompt. 14 means pay very much attention, or 1 means pay very little attention. I use 7 because then we can define also the parameters for image to image. So input image is equal to none, image path is equal to, I will define it with my image of the dog, which I already have here, and but for now I don't want to load it. So if we want to load it, we need to do input image is equal to image.open image path, but for now I will not use it. So now let's comment it, and if we use it, we need to define the strength, so how much noise we want to add to